Welcome to EDU World Space.
So in this video, we're going to talk about question 72 from chapter 20, which says, explain why HF is a weak acid, whereas HCl, HBr, and HI are all strong acids. So a weak acid is an acid for which the Ka is small. And remember, the Ka is the equilibrium constant for the reaction of an acid with water to form H3O plus and the conjugate base. So in this case, the Ka is for HF plus H2O forming H3O plus F minus. So in order for this reaction to proceed, the HF bond, the hydrogen-fluorine bond, must be broken. So if the Ka is small, we know that this reaction doesn't proceed very far. The equilibrium remains towards the reactants. So our hydrogen-fluorine bond is quite strong, and that's because fluorine is very electronegative. But that by itself doesn't tell the full story. So we know that we can relate this equilibrium constant that tells us about the strength of our acid to the Gibbs free energy with the equation delta G is equal to negative RT natural log of K, which is our equilibrium constant, our Ka. And we know that delta G, so that's how our Gibbs free energy relates to our equilibrium constant, but the factors contributing to our Gibbs free energy are the enthalpy and the entropy. So let's talk about the enthalpy and the entropy of this reaction. So we already said that because fluorine is very electronegative, we have a very strong hydrogen-fluorine bond. And breaking that bond causes our delta H, our change in enthalpy for this reaction, to be very positive, which means that our Ka, our equilibrium constant, is smaller. So a larger delta G would indicate a smaller Ka, and a more negative delta G would indicate a larger Ka. But that's not the only contribution to our enthalpy. We also have to consider the enthalpy of hydration. So the enthalpy of hydration actually has a negative contribution to delta H. So that actually brings our Ka back up to a larger value. So how do we account for this? Well, we also have to consider the entropy of hydration. So because fluorine atoms are very small compared to chlorine, bromine, or iodine atoms, remember as we go down the periodic table, our atomic radius increases and we have more shells, inner shells of electrons in our atoms. So we have these very small fluorine atoms, and the entropy for hydrating for water molecules surrounding these fluorine atoms in a very ordered way is a negative delta S. So delta S is negative, which means that we have a smaller Ka and a weaker acid. So this entropy of hydration actually explains why hydrofluoric acid is a much weaker acid than hydrochloric, hydrobromic, or hydroiodic acid.